Okay, so good morning, one and all. I know some of you, I don't know a lot of you, but we will know each other, hopefully, over the days. My name is Elette Boyle. I'm a faculty member at, this is a little bit of a confusing one. So it's IACR-CROSSING. It's a school in Israel who recently changed its name to Reichman University. And in addition, I'm also a senior scientist, part of the time for now, at NTT Research. But more importantly, what I'm going to be telling you about today is something called expander graphs. It's possible that some of you guys have run into these things. But if not, then hopefully this is something that comes up all over the place. It's a subset sort of graph theory of very useful types of graphs. Okay, my goal for today and tomorrow, so it's a two-parter, is going to be to give you at least a high-level flavor of what are these types of graphs, what are some useful properties about them, and then mostly focusing, so for tomorrow, on applications directly to cryptography, to secure protocols, and beyond. So I'm also going to give you little tidbits of things even outside of cryptography. For example, applications in error-correcting codes. Okay, and the whole thing, I'm not going to go super deep into anything, but mostly the idea is to try to give you a high-level idea, a flavor, and also to help you kind of direct into different areas of if you want to learn more. Okay, let's start out at the beginning, okay? A good place to start. So this is indeed, I'm going to be talking about graphs. Graphs in the sense of a standard sense. So you have some vertex set V. I'll use the notation mostly that there's n vertices. And E is going to be an edge set. So for example here, if I have, this is vertex U, this is vertex V, and there's an edge between them potentially. I'm going to only be talking about undirected graphs. Okay, so actually U comma V versus V comma U, I'm just going to sort of use those interchangeably. And indeed, so given such a collection, so I'm giving you a vertex set and I'm giving you a subset of all of the possible pairs of these vertices, and these correspond to edges that do exist versus ones that we don't have. Okay, now so if I give you such a graph, we can talk about things like what are the neighbors of a vertex? Okay, so if I have some vertex V, say this is my vertex little v, actually it's a little hard to tell in this graph, but the neighbors of V will be all of those vertices that share an edge. Okay, so for example, this one and this one are neighbors, but something over there that does not have an edge directly is not a neighbor. Okay, and this extends also if I have some collection, some, say, set of vertices, say this is S. Okay, I can talk about what is the neighbor set of that set, and this is really just kind of combining the union of everything. And note, by the way, that this can also include elements of S, if for example, I have edges inside of S. Okay, and we'll talk about the degree of different vertices. This is just how many neighbors does any vertex have. Yeah, so this is the size of the neighbor set here of V. By the way, also I should stop here for a second. I want to make this is like a school, this is a class. So if you have questions, feel free to ask. In fact, it's possible that I don't have an hour and a half worth of material. We'll see how it goes. So feel free to jump in if there are things that you want clarification. You are probably not the only one. Okay, and one last terminology for this slide. We'll say that a graph is deregular, okay, if the degree of each and every one of the vertices in the graph is exactly equal to D. Okay, so regular in the sense that every vertex has this property. Okay, and collectively, so the graph itself, what is that? This is the pair of the vertex set and E. And my animation appears to be in the wrong order. But here's an example of a vertex U and a vertex V. Okay, so this is like a very sort of combinatorial version of things. And it turns out that you can also connect graphs to matrices and linear algebra. And we'll see an explicit case of that, okay? But let me start by saying, given a graph, such as this beautiful graph right here, how can we potentially get a matrix from this? And the kind of the canonical way of doing that is referred to as the adjacency matrix of a graph, sometimes denoted A sub G. Okay? So what is this? This is some square n by n matrix. Remember, what is n? N is the number of nodes, the number of vertices in the graph. Okay? And every single entry of this matrix will be either 0 or 1. When is it 0 versus 1? Okay, well, think about, here I'm listing my n vertices here, and also listing my n vertices to the side. And in a coordinate I comma j, I'll have a 1 in that position. Actually, maybe if you sort of like sat 30 seconds and thought, what should the definition be, right? The definition is that you have a 1 in this position exactly if there exists an edge between vertex I and vertex j. Okay, so for example here, if I'm looking at 4, comma 3, I have a 1 because there's an edge between 4 and 3. Okay, but I have a 0 between 3 and 5 if you look at that. Okay. And one thing to observe here, maybe this is a little bit redundant even, right? So I said I'm only going to be talking about undirected graphs, which means, if you recall, so it's not like I have a direction that 3 is pointing toward 2. It's just that 3 and 2 are connected. So what that means is that if I have, or rather I will have a 1 in position 3, comma 2, if and only if I have a 1 in position 2, comma 3. Okay, so this matrix is going to be symmetric. Okay. Okay, one more thing before we get to, the juicy stuff, right? Another kind of terminology I want to introduce. So this is a special type of graphs that we call bipartite graphs. Okay, so in contrast to these general graphs, they can look like whatever. Some things can be connected. Anything could potentially be connected to anything else. We say that a graph has a bipartite structure if the following holds. Okay, and this is like, this picture is supposed to kind of trigger. So bi coming from 2. The idea is that there's 2, you can sort of separate the vertices. So all of these are vertices, right? But you can separate them, partition them into 2 smaller subsets. I'm going to denote this by L and R just because left and right are kind of convenient. Okay? And tell me something, given this example, tell me something about what's special about splitting this split from L to R. What do you see about the edges here? Okay, you guys are quite group. Okay, well, in particular, I don't have any edges to and from L, and I don't have any edges to and from R. All of my edges are coming only from one side is from L and one side is from R. Okay, so any graph that happens to have this property happens to be a bipartite graph. Okay, so here's a mini question for you guys. So remember now the adjacency matrix of a graph. This is for general graphs. Suppose that I'm doing the adjacency matrix of a bipartite graph. What's something kind of special about this? Okay, well remember I've got all of the vertices here and all of the vertices going across. And sort of think about splitting that into the L part and the R part. And now I've got these 4 chunks. Okay, I've got the L part. And exactly because this is bipartite, I know I don't have any edges going between L vertices. So what that means is that in this entire region here, I only have zeros. Okay, and similar here for R and R, that I don't have any edges going between something to something in R. Okay, whatever this gray is, well, this can be kind of whatever. This depends on what are the actual edges that exist between these 2 sets. And remember that this is still a symmetric matrix. So whatever this gray thing is, this is some zeros and ones here, the exact same thing but flipped on, kind of rather reflected, will be up over here. Okay, so any questions so far on kind of terminology?
So the L doesn't have to be contiguous, right?
This microphone, sorry. So
the L doesn't have to be contiguous, right? Like it doesn't have to be a rectangular chunk.
Yeah, that's true. I've sort of, yes, you're right. So for example, it could be that I swap rows and columns or something. The question is sort of the ordering of these. Is that what you mean?
Right.
Yeah, exactly. So I've kind of chosen to order the vertices in a convenient way that has this structure.
I see.
But you're right. Honestly, the matrix itself, at least the properties they were interested of that are sort of defining the graph, aren't so connected to like whether I change the order of things. As long as I'm consistent, whatever the ordering here is here, like maybe should be the ordering now.
Thank you.
Any other questions? Okay. Okay, so we have come to the moment. I have, given you some general things in graph theory, but I promised to come here and tell you about expanders. So what are these? And I'm going to start high level and get, slowly more and more technical about this. But the first message and the most important maybe takeaway message here is that expander graphs are graphs that are potentially sparse in the sense that maybe they don't have a lot of edges going back and forth, okay? But still, even with that, have strong connectivity properties. Okay, so on one hand, for example, we have the fully connected graph. This is the clique on some end nodes. One, like a sparse expander might look something like this. Okay, again, this is keeping just a high level. That somehow it still is kind of connected in here. As compared to something, this is an example of something that is not an expander. And what is the problem with this? Why is this graph, why do I say this graph is not strongly connected or highly connected? Because, for example, it has this, like a bottleneck here, that there's only a few edges going across that connect over here to over here. And we'll see that there's a lot of properties such graphs like this will end up being quite different from graphs like this. For example, just to keep in mind, suppose that I start on one side and I start taking a random walk on the graph, okay? The fact that there's very few connections going from here to here means that if I start on one side on this graph and I take a random walk, it's going to take a long time before I'm able to get from outside of this side that I get over to here, okay? As opposed to here, if everything's sort of smeared around and everything, if I start somewhere and take a random walk, it turns out, spoiler alert, that in a good expander, after actually not so many steps, you'll end up getting roughly uniform across the whole graph. Okay, so these are something high-level things to keep in mind. Okay, so this is the high-level idea. And now the question is, how can we formalize this? What does it mean to have strong connectivity properties? And the answer is that actually there's a few different ways. There's at least 3 different ways of defining the expansion of a graph. Each one of them has slightly different properties, but they're all quite tightly connected. Okay, so they're not identical. But for example, if you're a good expander with one definition, then you'll also be a good expander with the other definitions. Okay, and so as I claimed and I mentioned, and we'll follow this up tomorrow in the second part of the talk, these types of graphs, these expander graphs, have a lot of applications. It's something I want you to have this in your mind when you're approaching problems and you get stuck somewhere, and maybe you're working with a graph, or maybe you don't even sort of expect things to come up, and keep this in the back of your mind as a tool, okay? In a lot of cases, like, okay, I need some good property, for example, with graphs, and expanders are, shockingly high percentage of the time can give you an answer. And just as a flavor, so they pop up in error correcting code design and de-randomization of algorithms and distributed computing protocols and other areas of cryptography. Okay, so let's say make a game plan. So for today, I have a few different topics. Again, so tomorrow I'll be talking about applications. Today will mostly just be about foundations, about the graph theory itself. Okay, and I'm going to split this into 4 parts. First, we'll go through and we'll give formal definitions of expanders, a couple, and talk a little bit about the connection. I'll say a little bit about existing constructions. I brought up this bipartite graph. Up till now, it's not really clear why did I talk about bipartite graphs. So you'll see this. There's actually kind of two types of expanders. I'll explain this a little bit more. But the second type will be this bipartite expanders. And then at the end, we'll close up with some useful properties of these graphs. Okay. So good. So any questions or games? You're pumped for this? Yes, let's define expanders. Let's do that indeed, okay? So first up is formal definitions. And so as I just mentioned, in fact, when you say the word expander, sometimes it's a little fuzzy, and sometimes actually people mean sort of standard expanders, and sometimes, depending on context, they might mean something that's a little bit of a different definition, which are these bipartite expanders. I'm going to, for now, up until mostly the end, I'm going to focus just on the standard type. So we're not going to have any sort of bipartite structure. And in fact, in some sense, you kind of don't really want to have a bipartite structure if you want this kind of expansion. Okay, and also one more thing I'm going to put out there. I'm going to be talking just about deregular graphs. Okay, what D is, that'll vary, but it'll be convenient to think about that every single vertex in the graph will have the same degree D. Okay. So in regard to these different definitions, I remember learning about this for the first time, and in my mind, it's not obvious at all why these definitions that you're about to see have anything to do with each other. Okay, and yeah, we won't really actually get very deep about where do these connections come, but I will tell you, and you'll have to trust me, that surprisingly so, they're very connected. Okay, so I'll talk about one example of a combinatorial definition and another that's algebraic. And one more thing that I want to do before getting started is that, so formally these definitions are sort of, it's not, okay, so I'm going to be talking about asymptotics, for example. But what is the asymptotic of a single graph? There's nothing. It's a single graph. It's finite. Okay, so kind of formally underlying this, we're actually going to be talking about families of graphs. But for example, you can think about natural classes. So here, first of all, family of graph. This is like, say, for every n, so this is the number of vertices, I have some associated graph G sub n. Okay, an example of a family of graphs would be the family of fully connected graphs. Right, like every single one has a different number of vertices, but it's the fully connected graph. Okay, and we'll be talking about properties of this family of graph sort of asymptotically with n. Okay, so this, let me know if this is confusing and I can try to explain a bit more. Okay, the first definition. So this is a combinatorial definition. It's actually not the only one, but I'm going to focus on this one for now, which is known as edge expansion. Okay, so we're starting with a graph, as we've seen. Now, yeah, see, now the formulas are gonna get a little bit heavier, but don't worry, we'll step this through. Okay, so I normally have a pointer, but I left it at the hotel. Suppose that I take a subset of vertices, okay? For that subset, I can consider this notion, I'm going to call Hg of S, okay? Which corresponds to how many edges, or rather what sort of weighted fraction of edges are there going from S outside of S. Okay, so remember that if I have this set of vertices S, there might be a lot of, actually, here's a good first question. Suppose I'm, oh, thank you. One moment, please. Perfect, perfect. Okay, good. Otherwise I have to start jumping up, right? Okay, so yes, this expression here. So here's the first, before this, if I have a deregular graph, right? And I'm looking at a subset of edges, subset of vertices S, I actually know exactly how many edges those vertices have in total, right? Each and every one has D. So if I just kind of added that all up, I'd have D times the size of S. Okay, but some of those edges stay inside of S. Some of the edges go from S outside of S, going from S to S complement. Okay, and this is what I'm interested in here. How many edges go outside of the set S? And in particular, what fraction kind of the number of vertices are there? So for example, this could be 0, right? Say that all the edges stay inside of S. Could be bigger, bigger, bigger. What is the maximum that it could be? Well, the maximum it could be is D, right? Because the total number of edges that S has at all is D times the size of S. So this is some value. And in some sense, to have good edge expansion, what we want is that for any S that's not too big, okay, that this value is going to be relatively large, that you're not stuck inside the same thing. Okay? So this is formalized as follows. So this, remember, this is a property parameterized by some set S of vertices. Now the property of the graph, so this is the definition of this thing here, is the smallest of this over all of the possible S's. Okay, just a second. Not all of the S's, but all of the S's up to half the size of the graph. Why do we put this here? Suppose I didn't put this constraint. I just said any set S. Why would this be a problem? Yeah, for example, if S is the whole graph, this has to be 0. There's no edges going outside of the graph, right? As soon as I kind of get too big, I don't have much to spread out to. So I can't expect the number of edges going out to be that large. Okay, so kind of intuitively, we're only going to consider sets up to, say, half the size of the graph and try to figure out how many edges are going across there. Okay, so here's a picture, again, of the set S, and these are the edges that we're interested in, and weighted as a fraction of the size of S. Okay, so here I've defined this thing. Again, we know that for any individual S, this value goes between 0 and D. So in particular, if I'm looking across the graph over all of these S's, this will also be somewhere between 0 and D. Okay? And now going back, so remember, so all of these three are for one fixed graph. And I want to say, when is this family of graphs expanding? So intuitively, what I want to say, what this line is saying at a high level, is that for as I'm getting bigger and bigger in the graphs, this value, this sort of edge expansion of G sub n, okay, that's this, does not go to 0. Okay? Rather, what is the opposite of not going to 0? That there exists some constant greater than 0, such that I never get smaller than that constant. I'm sort of always stuck away from 0. Okay, so again, let me do a recap on this. So this was defining for a fixed graph. I have some notion of how much are of like any potential subset that's not too big, what fraction of edges are going out. Okay? For us, it's good if this is a big number. We want this to be big. And we're saying, so for this family of graphs, this is going to be called an expanding family of graphs. If I'm not even demanding so much, right? I'm not demanding this is close to D or something very large. I'm just demanding that this is bounded away from 0. Okay, this is a bit to swallow. So, oh no, my animations. Okay, well, pretend like you don't see this. Question, okay.
We have this symbol H for this ratio. Why is it the letter H and not E for edge expansion?
You know, it's a good question. I don't have a good answer for that. Actually, does somebody else know? Okay, for now we'll leave it as a mystery. I guess E is taken just for edges. I'm not sure why H is a better option, but but it is relatively standard at least. Question.
So this last line, do you want it for all n or like for all sufficiently large n?
Okay, fair enough. Yeah, I guess it mostly matters sufficiently large n, but you might as well, like, basically the initial ones would not be kind of very good expanders, and this is just demanding that everything is at least that good.
Yeah, so just intuitively the question is like, as n increases, it's supposed to go down. The h of the number is expected to go down.
Oh, I see, I see. So in general, you'll see an example that's not necessarily always the case. But as n gets bigger, it's a little bit harder potentially to get expansion. And we're just demanding that maybe you could actually get up and down or maybe even go bigger. Okay. Wait a second, in the next slide, we'll see one where it actually gets bigger as we go. Okay. But the requirement is that you don't ever get asymptoting to 0.
And a second kind of related question is, if you fix n,
yes,
and you increase the size of s, is there some, like, is it also expected to decrease, or also it's not, no?
As far as I know, I don't think people look so much at that. I'll come back to that much later when I talk about bipartite expanders. Actually, the definition there is more of a scale in that sense, that it's like 2 parameters, that instead of just stopping at n over 2, it's a trade-off, for example, maybe, that if I stop smaller, maybe I can expand more.
But I think the stopping at n by 2 is like s and s complement, one of them will be n by 2 smaller. So I don't know if it makes that much importance. For
that is quite natural. And then maybe in the bipartite case, you don't have exactly that because of the 2 sides.
Yeah, thanks.
Mm-hmm.
Does a family of graphs only have one graph per n?
Sorry, can you say that again?
Does a family of graphs, defined this way, only have one graph per value of n?
Yes, and in fact, I'm cheating a little bit. You don't even necessarily need to have one for every natural number. You could have it like you can consider families of graphs maybe for every even number I have a graph or something like that. But indeed, at each sort of level, whatever those levels are, I'm thinking of a single graph with that many.
Thanks.
Mm-hmm.
Hi. So I was wondering if there's some sort of like, if you could give us maybe some intuition as to like which part of this definition, I guess, imposes this restriction on like the number of edges in like the sparsity?
It doesn't.
Okay.
This so far I have not put any, you're right, I have not put any sparsity condition here.
Okay.
So this is going to, in fact, in the next slide, I'm going to do a couple examples. One will be the fully connected graph, and we'll see it does great in this regard.
Okay.
So yeah.
All right, thank you.
So maybe one short question. So this H is defined over all subsets S for a particular graph, right?
Correct, up to size n over 2.
Right. Can we efficiently compute this? Because it would be like exponential, right?
Good. Okay, good. I'm not going to talk, or I haven't planned to talk about it. You were very right. And in fact, in general, the problem of given a graph, trying to decide if it's a good expander or not is NP hard.
I was just thinking about alternative definitions of expanders. So you could imagine a family of graph where for sufficiently large n, when n is even, then you're above epsilon, and when it's odd, you're below. Like, and it just alternates all the time. Like, would this somehow be satisfactory already? I mean, of course, it would be a weaker definition. But then to counter that, like, you could consider it and have a conditional, like the inferior limit of h of gn could be greater than epsilon. So I'm wondering about the connections between these 3 possible, for instance, definitions.
So to address the first kind of candidate that you had, Actually, the truth is, you're right that there's something interesting there still. And essentially what would be the case, this is going back to what I mentioned, that I'm writing this, that for every natural number you have a graph, but it's actually still very interesting if this can be parameterized by any monotone increasing subsequence of n. So for example, if you just throw away the ones that are bad, you would get a family of graphs that does not have every n represented, but would match this definition. So this is kind of what people would study then, that version.
Okay, that's good. Thanks.
I have a theory from where the H comes from.
Good. I'm happy to hear.
Expansion in Hebrew means hachaba. So it starts with hey. That's my conjecture.
I
but
like
I don't know.
Yeah. Nice. Okay, cool. So yeah, apologies if this is jumping up a lot, but I want to go through two kind of, simple-ish examples of practicing with this definition, this edge expansion. Okay, the first example, really this is animated, is the clique. Okay, so let's take a look, stepping step by step from the definitions of the previous slide, with a slightly different notation as well. So this was like the HGS, I put it subscript here, okay? So suppose that I have the clique, and now I'm looking at arbitrary, so take an arbitrary subset S up to size n over 2, okay? Say this S. And now the question is, what is this expression? Remember, we're interested in the number of edges going out, so going outside of S over to S bar, divided by the size of S. Again, if I'm the fully connected graph, we can actually compute how many edges do I have going across here. Okay, well, for every single vertex in S and every single vertex in S bar, there's an edge. Okay, it's fully connected. So what does that mean? That means that the number of edges going across is going to be the size of S times the size of S bar. For each of these pairs, I have a distinct edge going across. Okay, well, this ratio, now, remember I scale it out by the size of S, this gives me the size of S bar. And since we're taking all the S's of size up to n over 2, okay, well, now it's like taking the minimum of the size of S bar for these, and this is going to be n over 2. So this is smallest when I have the biggest S. S bar will be n over 2 size. So good. So taking a step back, well, this looks a little weird, and indeed, this is why it's more interesting when we don't have these super connected graphs. But I do want to emphasize that the family of cliques does satisfy the definition, hardcore, in a very strong way. Okay? So why? What was the last step, the last piece of the requirement? Was that for that there exists some constant epsilon, okay, such that this expression, h of g, is always above epsilon. But h of g here is n over 2. So in fact, not only is this not going to 0, this is not like, I'm not worried about crossing some constant epsilon going to 0. In fact, this number is getting bigger as we get bigger. Okay, so this is one example where it does satisfy this edge expansion. Okay, before getting down here, any questions about this example? Okay, yes.
We assume that the graphs are deregular, so it's not a constant in the family, but each graph itself is
good. That's a good point. I'm going to consider constant, yes. Okay, so you're right that that's different. I see. Fair point. Okay, so it's let me say you can consider it where the degree is a function of n. It will be, so the interesting thing is that it will be possible even when it's a constant. This is the more interesting case. Good questions, by the way. Okay, so let's do another example, which is this friendly guy from the previous slide, which I claim to you is not an expander. Why is this not an expander? Let's take a deeper look. Okay, so more specifically, suppose that I have this blob here that has n over 2 edges, and this blob has n over 2. And suppose that the number of edges going across here is square root n. Now, let's consider this hg of s. What's a potentially bad choice of s up to size n over 2? For example, this. Okay, so suppose, let's consider this being my s. This certainly is an example of a subset of up to n over 2 vertices. And for this specific choice of s, I know that the number of edges going from s to s bar is this. It's just square root of n. Okay? So what do I have? I've got that this is square root of n over 2, because remember, we always scale by the size of s. And here, this is really kind of trying to represent that the number of edges going out as a fraction of the total kind of mass that I'm starting with. This ratio will indeed go to 0. Okay, and that means, so this was for a specific example, S. This means that this property for the graph will also be the case. Will also go to 0, which means that this sort of viewing as a family of graphs where for each n I have some different blob, but each one has the property that I have square root n edges going across. Okay, so any questions about this? This is an example of something that does not satisfy the edge expansion definition. Okay. Okay, so this what have we seen now over the last 2 slides? Again, we were talking about one combinatorial definition of graph expansion, this edge expansion property. Let me just mention, I'm going to talk about it a little bit more later on, not so much now. There's another combinatorial property that people can define, which is some form of vertex expansion. Okay, it's like instead of saying I have a lot of edges going out, it says that I have a lot of distinct neighbors, which is not necessarily exactly the same. Okay, so put that to the side for now. But what I want to go to next is a definition that looks totally, totally different. At least it did to me. Okay, so the previous was combinatorial. It was talking about I've got these edges and I'm looking at this graph structure. This definition is pure linear algebra. Okay, and indeed, so where is linear algebra coming from? Well, remember this matrix, this adjacency matrix, that given a graph, I can always consider some n by n Boolean matrix. Okay, and you know, what are you doing? You're on a Friday night, you've got nothing else to do, you've got yourself a square matrix, you might as well ask, what are the eigenvalues of this matrix, for example? Okay, and just a recap, so remember, what are eigenvalues of a matrix? This is values lambda, such that they're, so for some vector x, I'm viewing this now, I'm doing think of, so x is some vector like here, and I'm multiplying it by this matrix. And the question is, for certain directions x, if I take x times this matrix, I'll get another vector in the same direction, but potentially longer or shorter. Okay, and this longer or shorter, this is the eigenvalue. And this, sort of out of interest, this is the corresponding eigenvector. Okay, so it's maybe kind of out there, a bit of an odd question. Let me claim to you that without knowing anything about the graph, except that it's deregular, we actually know already one eigenvalue of this matrix. Okay, to do that, let me quickly go to the whiteboard here. Okay, remember being deregular, so what does this mean? This means that, that every vertex has exactly d neighbors. In particular, for example, every every column, and also, in fact, every row, has exactly D1s. Now, suppose I take the vector 1, 1, 1, 1. Maybe this is length n. This is like my x. What is the output of this multiplication? Okay? What is this? What is the first position? Remember, the first position, I take 1, 1, 1, 1, 1, 1, 1. Here I've got zeros all around, but I have D1. Okay, what is that sum going to be, this inner product? D. Right? Now, column 2. D, okay? Nothing fishy going on. In fact, in every single position here, I'm going to get contribution of exactly D1s in the inner product. Because here in this case, every single column has D1s in this matrix. Okay, well, this looks interesting. This is some vector x times the adjacency matrix AG. And this is equal to D times the vector x. What does that mean? Bam! That means that one of the eigenvalues of this matrix is D. Okay? And it turns out that as long as your graph is connected, D will actually also be the biggest eigenvalue. This kind of makes sense, right? It's like I want to somehow, I'm not really going to be able to blow anything up more than times D in a sense. This is not a proof, but maybe a little bit of intuition. And so the top eigenvalue, the biggest one, is D. And the question is, what is the next biggest eigenvalue? And this is where the actual structure of the graph, where are my edges coming to and from? This is where that comes into play. Okay, so let's define lambda. So lambda 1, this is D. This is the biggest eigenvalue. And let's define lambda 2 to be the second biggest eigenvalue. Here an absolute value. So if it's positive or negative, I don't really care. I'm interested in what is the absolute value of the second eigenvalue. Okay? And so this spectral gap is the difference, the gap between the top and the second highest. This is what's called the spectral gap of the graph or the matrix. And it turns out, if this gap is big, this graph is an expander. Okay, so first of all, it's by definition. Actually, this is the definition that you can think of here. If I have a family of graphs, this is some sort of parameter on the expansion. Okay, it's saying you're sort of bounding that your second highest eigenvalue can't get too close to the top one. And maybe the shocking thing here is that, so if I define this definition is not so important, I think. I'll put the next slide. Just kind of keep in mind that the thing that one of the metrics is how big is this gap, okay? And what's mind-blowing in my mind is that you're a good expander in the edge expansion case, if and only if you're a good expander in this spectral gap case. And this can be, so what is this? It's not exactly one-to-one. It's not like you have exactly the same numbers carrying over. There's a little bit of loss in what can be claimed. But for example, so remember this h of g, this was like this property for the graph, like the worst case over all these s's. This value is stuck in between two expressions that depend exactly on what we just introduced, this gap between, this is the highest, the top eigenvalue and the second highest eigenvalue. Okay, and some other, constants here. Remember, d is the degree of this graph. But what this means is that, this concretely gives you some sort of range. They're correlated with each other. And in particular, what that means is that if this is very big, for example, then this has to also be very big. And vice versa, if this is very big, then this can't be too small either. Okay. Okay, so I want to kind of close up a little bit on the first part. And what have we seen so far? So there's these two different definitions of expansion. One is purely combinatorial, taking a look at these subsets of vertices and considering how many edges are going outside. And the second, which is purely a linear algebra type of definition, looking at the highest and the second highest eigenvalue. Okay, question, yeah.
Okay, so like the type 1 definition, you said it's NP hard, but type 2, I think you can calculate the eigenvalues, right?
Yeah, good point. Just a second. Yeah, I think I'm wondering if that. I guess that must be it. That it's not exactly. Yeah, it's a good question, actually. I need to think a little bit about it. I guess maybe as a pseudo answer is that this gives you some kind of connection of between these things, but not exactly tight. But it's a good question. I don't know, I'll get back to you tomorrow about it.
I think I was just thinking, is that the deregularity playing a role? Because when we say expand of a graph, there is a generic graph, and this is a deregular graph. So maybe the two have different properties.
So I say that again, but.
So I think from what I understood, for a generic graph, not a deregular, but a generic graph, it's NP complete. But maybe for a deregular, I'm not sure, and maybe this.
Yeah, I guess the question. So in general, I see. Yeah, I should know the answer to this, but I don't. But it's part of it. I'll look into it.
I also have a question. Is there some connection to like edge connectedness of the graph, whether it's a good expander or not?
By the edge connectedness, what do you mean?
How many edges you need to cut the graph in two parts?
Yes, yes. In fact, actually, if you take a look at this definition of the edge expansion, this thing is, so kind of ignore everything else. For example, what is this expression? This is saying like, this is equivalent to going over all the cuts in the graph, right? That aren't too kind of, say even all the cuts in the graph. And considering the edges, like what is the cut, the number of edges going across the cut, and scaling it by the smaller side. That's exactly what this thing is.
Okay, thanks.
Sorry, I just looked it up. I just wanted to confirm that computed it exactly is actually co-NP hard. So I think it's hard to get a witness that you have a particular value. It's the other way around, whereas indeed you can approximate it.
But then, okay, the question though still stands, doesn't it? Can't you show, so this is also for deregular graphs. Can't you also show that the eigenvalue second eigenvalue is very high? Or is
yeah, I don't know yet. So
okay, I'm at least happy. Yeah, this is I'm not the only one. Cool. Okay, so I want to give a little bit of a flavor next of the types of constructions that do satisfy this. And this also kind of goes back. So of course we saw that the family of cliques has great edge expansion, but this doesn't really give us what we want, right? The whole goal is to have something that's not the full cost of lots and lots of edges. And it turns out we don't have to try very hard, which is fantastic, okay? That a random graph actually has this property with high probability as long as the degree is not too low. And this is kind of amazing, right? So the statement is that if I take a randomly chosen deregular graph with d greater than or equal to 3, then in fact with high probability over n here, that this will have good expansion. And note that this is not the case for 1 and 2. So for example, 1 might not even necessarily be connected. Will. Okay. So a little bit of a side note here. Note that I'm automatically, during this process, I'm choosing something that is deregular. This is a stronger thing than maybe what you've seen of other random graphs, like this GNP graph. So this is a distribution on random graphs where I take every single edge with probability p and don't take it with probability 1 minus p. Okay? If you're looking at that, then you actually need to push p up a little bit higher than what would be the equivalent of like 3 divided by n, but this is just for the randomness to get concentration bounds. Okay, if you didn't follow that, that's not a problem. But here, if I'm only sampling graphs that already have the right degree, then it becomes much easier. And one of the really, really fantastic things about this, going back to one of the questions that came up, is that instead of something like the Clique, which has a lot of edges, n squared edges, okay, these graphs have order of n edges, okay? For example, each node only has 3, so I can't possibly have more than 3n over 2. Mm-hmm.
When we're choosing the graphs randomly, are we choosing from the family of like connected graphs, or are we like,
Okay, good. So if you, I think it should be the case that even if you take, that's a good question. I think even if you take just from an arbitrary 3 regular that you should be connected. I'm not fully sure about that. Okay. If not, then yes.
Hello. Could you expand a bit more on what does it mean to say randomly chosen deregular? Is it
Sorry,
like...
I still can't hear very well, actually. Can you make sure that it is on? It's on.
Okay. I'll just take this off. So, what is randomly chosen deregular graph? Is it like set of isomorphic graphs and you're choosing one of them uniformly at random, or
so they're not necessarily isomorphic. You could have different sorts of structures, but it is the case that that they're all 3 regular.
Okay.
So yeah, I also wanted to ask, like, how you sample these graphs. Do you like take vertices and then sample edges as long until you have d edges for each vertex, or like how does it work?
Okay, good. Yeah. So this is like a very clean statement, but it's kind of complicated. Yeah, it's not really clear. How do you sample a 3 regular graph at random? So honestly, in practice, what you'd probably do is take a GNP graph where p, so you have to crank p up a little bit. It'll end up being, for example, like you can get log degree or something like that. Basically, so p would be something like log n over n. And then if you take that at random, then you will get as well.
Okay.
This is one example of a simple way of doing it.
And so directly related to this question, something I would have tried to do would be to say, okay, for each vertex, I look at, well, every n minus 1 to 3 possible other sets of 3 edges. I put those 3 edges with probability p all the time, and I would have computed p for which, I get that probability 3. With a high probability. That's how I would have done it. I mean, another completely non-constructive way to do it would be to say, okay, well, I look at all the graphs which are 3 regular, and then I sample one uniformly at random out of them.
Right. So I guess the question is kind of how to build that list or something. But I think you're right that some approach of the previous, I'd have to think about it a little bit, but can probably give you a random sample from that.
So how would you? What did you have in mind?
What did I have? I'm a theorist. I had in mind that there is magically a sample from this distribution. Okay, so let me think. So I guess actually we need to verify that this does work, but maybe what you were just suggesting, right? That for example, the first vertex, you choose a random 3. Then you kind of, like for the second vertex, and then once you use up a vertex, it's no longer in the, seems like that should be random. Okay, cool. But in any case, kind of, and this, even beyond the specifics and everything, the punchline here that you should really keep in mind is that random graphs, as long as your degree is not too small, that random graphs are good expanders. Okay? Which is also good news. That means that there's lots of expander graphs. But of course, in some cases, we don't want to just have random, or maybe we would want something that we can guarantee that we get is an expander. Not just that, okay, I've sampled this graph, probably it's good, I'll cross my fingers. So there also exist explicit constructions of expander graphs. And perhaps the original one, it was back in '73 due to Margulis and analyzed later on. I'm not going to analyze this, but I'll just give you kind of a flavor of one type here. So for example, the vertex set in this graph is actually like each vertex is a pair of numbers, right? So here by Zn, I mean the integers mod n. So I have between 0 and n minus 1. And for each pair of I comma j, that corresponds to one vertex in this graph. Okay? So how many vertices do I have? Okay, well, maybe this is a good point of indexing by n. I actually have n squared vertices here, right? Okay, and the graph is defined in a very, very structured way. So every single x comma y, this is one vertex in my graph, has 8 different neighbors. Okay, and each of these, so I'm getting 2 from each of these pairs because I have either the plus or the minus. And what this is coming from is some function of the x that I have and the y. Okay, so for example, x plus 2y or x minus 2y comma y, and so forth. Okay, so every vertex, I suppose, aside from 0, which has a bunch of self-loops. Okay, and so I'm not going to go much deeper. In fact, I want to still cover a number of other things. But let me just say that this is an example. This actually is a very structured graph. And you can show that it's at least a decent expander. Okay? So here, for example, remember, one way of saying that this is an expander is talking about if you look at the eigenvalues of the graph. So what is the highest eigenvalue here? Remember, it's the degree. It's going to be 8. Okay, so the second highest eigenvalue, you can prove that this is bounded above. It is not larger than 5 square root 2, which is also kind of a big number, but there's a constant gap at least between 8 and this number. Okay, another approach, and by the way, there's a lot that I'm not covering. If you're interested, you should take a look. There's a whole class of graphs, these Ramanujan graphs. I'm sure you've heard of Ramanujan. He's done a lot of really cool things in math, and one of which is designing this explicit construction of expander graphs. And so another thing that I want to mention here is sort of a procedure for building up. And this is what's known as the Zig Zag Product. Okay, so this is a procedure where you sort of step by step, you start with 2 smaller graphs. And here, actually, this is one example. This is one graph. This is another copy, an identical copy of the same graph. So there's going to be an inner graph and an outer graph. And somehow this is going to allow us to build up to a bigger graph that preserves the expansion up to some amount. Okay, so suppose that we do this, and they did, in fact. So this was awarded a Gödel Prize in 2009. Then this is fantastic because at the very small level, we can sort of brute force it. If I have a small number of vertices, I can just try lots of graphs and find one that has pretty good, expansion properties at the small level. And then I can get these bigger classes of graphs by taking this and kind of repeatedly operating with themselves. Okay? So what is the operation? Well, first of all, so it's starting with this pair of graphs. One is G, one is H. So G has n vertices, degree m, and some second eigenvalue lambda. H has m vertices, some degree d, and some other second eigenvalue. And so this represents some new graph. I'll say a few words about it. I'll kind of describe what's going on. It's going to have n times m vertices. The degree will be d squared. And the second eigenvalue is bounded. So there's actually an explicit representation, some formula as a function of lambda and lambda prime. But in particular, for purposes of this talk, it's not too big. So you're not losing too much. Okay? So, good. Okay, so here, so what is this operation? It's going to take, essentially, so as I said, think about H as this outside graph. Okay? So I have nodes for each, so I have vertices in this graph. And each of these vertices, I'm going to expand out. Okay, so this was some u in the original graph. This was some vertex v. Each one I'm expanding out and putting a copy of the second graph. Okay, so first of all, why does this give me n times m vertices? Well, I had, say, for each vertex of the original, now I'm expanding this out to the number of vertices of the second graph. So this is where the product is coming from. Any questions so far?
Just about the expression. So now we really don't need, I think, H to be an expander, right? If we want, because like the degree is like growing, like getting squared each time somehow, and then the eigenvalues are just adding up. So if I just keep doing this, then I can make the degree way bigger, and then.
Yes. In any case, it's a good process.
Yeah. So here, like, we only need G to kind of be a good expander, and then we can do it many times and get like a big expander. Or?
Yeah, I think that should suffice.
Okay.
Okay, so continuing here. So what's going on? So first of all, we took each vertex of the original graph and expanded it out to an entire copy of the other graph. Okay, and where do I have edges in the new graph? Okay, well, I have the edges between where in the original graph these are now edges as well, and I also have edges going from here to here. Okay, so like each of the different things. Okay, so again, kind of the high level, this is a procedure that is very useful and allows you to kind of build up.
Sorry, can I ask a question? So
yes.
I didn't understand when you have an edge, like between which nodes in the two new graphs. Because previously we just knew that in G, these two nodes were connected with an edge, I suppose. But which out of the new vertices do you connect?
Okay, so
like in this case, 2 and 5, but why?
So so this is, by the way, this is where the Zig Zag product kind of comes in, and now I need to think about it. So you have an edge when you can get from so I think it's, isn't it like the case that you can get, so say, yeah, actually I need to remember. So let me not answer this now, I'll answer it afterward, but to get to the right degree, so it's not just, so here this is sorry, just a second. Okay, sorry about this. Let me take a look afterward.
No worries, thanks.
It's been a while since I've like actually used this thing. But okay, so in any case, minus many details, I guess keep in mind that this is a way of building up, but I'm happy to look into it. Okay. Okay, so up until now, we've been talking about these standard expanders. Okay, but I said there's also a sort of second class of these things that are bipartite expanders. And now I want to say a few words about these. Okay, so it's going to, so in this, in fact, as part of this, I'm going to sort of introduce a third definition, which you can also apply. You can also kind of translate it in a standard natural way to normal graphs, of going to be vertex expansion. Okay, so again, there exists a version of vertex expansion also for standard graphs. I didn't talk about it, but I am going to talk about it in this context of bipartite graphs. Okay, so let's take our favorite bipartite graph here. Notationally, say that n is the size of L and m is the size of R. And I do want to think of some sort of deregularity. For whatever reason, it mostly is the case that we consider deregularity on one side. Okay, so for example, for every vertex in L that I have the same out degree D. Okay. All right, so an NMD gamma epsilon bipartite expander graph. So we've just seen N, M, and D, and now let me tell you what are these two new parameters. Okay, this is a graph such that, okay, so for every S subset of L that's not too big, remember before our not too big was up to n over 2. In this case, we're going to consider a more flexible parameter. Okay, so gamma is going to be something here between 0 and 1, right? Some fraction of S. Okay, and you are a blah, blah, blah gamma alpha bipartite expander if for every S that's up to gamma n, the neighbor set of S, okay, is going to be greater than or equal to alpha times the size of S. So again, this is saying for any S on the left that's not too big, my neighbor set is alpha expanding from the size of S. And just a quick comment about this, the two similar but kind of different flavors of definition. So remember before we were talking about edge expansion, I was talking about how many edges come out of this set. And now this is a little bit of a different notion where I'm actually interested in how many different vertices do I connect to. Okay, so this is a vertex expansion definition. Okay, and another comment. So I said here, gamma goes from 0 to 1, right? It's some fraction of S. And what about alpha? So alpha, okay, could be, I guess, as small as 0. Actually, we know you have at least D neighbors, right? But what about, so I need this alpha times the size of S. So the question is, what fraction can we possibly expand out? And again, if this is D kind of left regular, then each vertex in S has D neighbors, I know that, individually. And the most you could possibly expand is that all of these D neighbors are distinct. So this would be saying that my alpha here is D times the size of S. Okay, another question. Do we want big or small gamma and alpha? Say I fix everything else and I increase gamma. Is that good? Say that it still holds. I mean, okay, let me clarify the question. Suppose that I have a graph that is gamma, alpha, blah, 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 and now suppose that I have another one that has bigger gamma and alpha, or like suppose it also holds for a bigger gamma. This is a stronger statement. This is a stronger requirement. So this is what I mean by better. Like if you can satisfy with a bigger gamma, that's a better thing. right? Because it's saying, for example, if I have very, very small gamma, then that's only giving me a property, it's only giving me a guarantee on very small subsets of S expanding out. If it also holds for bigger gamma, then it also holds for bigger kind of chunks S of L. And how about alpha? Big alpha is also good, right? It's spreading out more. I have even more neighbors. Okay? Question?
Maybe just to check that I understood. So if gamma is 1 over n.
Okay. So, so there are some things that can be said. Is there actually a... is there an eraser for this? Yeah.
It's on the whiteboard.
Oh, perfect. Blend it in with the board. So one thing that is always true, right? No matter what my bipartite graph is, if I'm deregular, then I do know that I am, so NMD, say I have gamma equals 1 over n, something. I claim no matter what the graph is, I already know I can stick something in here. What is that something? Let's take a look. So if I'm restricting to subsets S of size up to, so this is gamma n, right? This is equal to 1 over n times n. This is just subsets of size 1, right? So this, for example, this could be S, in which case I know exactly what the size of the neighbor set of S is, and what is that? This is D. Okay? So this is always true. For example, this is like on the one extreme, that if I have very, very small gamma, it's, in fact, is not telling me anything interesting. I can have, super great expansion, but, any graph satisfies this. Super great in the sense that this is big, but this is not so meaningful. Okay? And, yeah, so you can kind of, as gamma gets bigger, this becomes harder, right? So, for example, now already if I have 2 vertices, it could be the case that some of the neighbors overlap. So now it's a little bit harder to get bigger expansion.
Thanks.
So you said that if we fix alpha and increase the gamma, then it's better in some sense. Because if you increase gamma, then the number of sets S are huge, and the number of constraints they need to satisfy is also large. But at the same time, if you increase the size of the S itself, then there's a good chance that it will satisfy, right? Because there are more outgoing edges from S and...
But watch out. Remember that this here, it's true that you'll have more neighbors. In fact, you're only going to get more, you can't decrease neighbors, right? But in some sense, I need this to increase, like if I add an extra vertex into S, to get the same alpha, I need to add alpha new neighbors.
Sorry, yeah, S is increasing.
So the fact
that,
yeah, this is a good point to emphasize, actually. Yeah. That, again, this is not like you just have some number of neighbors, but your number of neighbors is expanding from S. It's like the size of S times alpha.
Yeah, makes sense. Thanks.
Good.
Another question, or maybe 2 related questions. Is the left size necessarily bigger than the left set? Is it necessarily bigger than the right set? And,
okay, good. So, good. Actually, I want to say a couple comments about this. First of all, you can kind of consider both regimes, where, for example, R is smaller, R is bigger. One thing to observe is that when R becomes bigger, this task becomes easier for us. Okay, in the sense that, like, if I have more options on the right-hand side, I have more sort of space to spread out to. So, for example, maybe I don't need these to overlap. I can have it be the case that I can put these neighbors down over here somewhere. To an extreme, for example, suppose if I have that the size of R is, for example, suppose it's equal to D times the size of L. Claim you can get an amazing, expansion with respect to this property. Why is that? Because I can build a graph even where each vertex has D disjoint neighbors. Okay, so as R gets bigger, this becomes an easier task. But in fact, in some applications, for example, directly in error correcting codes, R inherently needs to be smaller than L, in which case then it's trickier. You have to kind of work harder at that.
And a related question, can it be the case that we can switch the roles of L and R and get the same properties?
So it's a little asymmetric in the definition. For example, even just the regularity. But if you like forced it to be regular on both sides, if you force it to be regular on both sides and the sizes are, for example, the same, then okay. If you force it to be regular on both sides and the sizes are the same, then it is the same, right? Like it doesn't matter which I'm calling which. And I would imagine that probably the same thing should hold in the other direction. You have to think if there's like nasty cases that you can come up with. But okay, let me leave it at that. Sort of inherently, it is a bit of an asymmetric definition. But you'll see where it's okay. Like in applications, in a lot of the cases, they are playing asymmetric roles. So you really do want expansion going in one direction. So this makes sense.
Thanks.
Is there a question up there?
So does this satisfy the earlier definitions like trivially, or am I missing something?
Not very well, yeah. Yeah, this is why it's sort of a different definition. It is interesting actually because, as I said, in some contexts, if you just see the word expander, sometimes people are talking about bipartite expanders, but you have to like fish around a little bit to see that this is what they mean. Okay, let me see. Is there anything else I want to say here? So just one kind of final thing to mention for bipartite expanders. Once again, turns out random graphs of a given degree also are expanders with good probability. And this sort of kind of unfortunately messy expressions of like there's different trade-offs of what does the degree need to be versus what is the expansion as a function of the size of L and R and so forth. But let me, instead of going into a bunch of messy formulas, let me just say that first of all, you can prove that using turn-off bounds with a bit of work. And secondarily, that at least kind of keep in mind that random bipartite graphs are there for you, and you can look up to see if you're in a good parameter regime for that. Okay. Okay, so I'm getting to kind of the end of what I want to cover today. And the last part is to talk about a little bit more coming back to why do we care about expansion? What are some useful properties of these graphs? Okay, so I'm not quite going to get to the point of applications. We'll see that tomorrow. But at least maybe some properties that are useful. Okay, and the first is a sort of a direct one. Actually, it turns out the definition itself is useful. The fact, for example, that you have these expanding sets of neighbors, this already helps in many cases, and you'll see this. So for example, for the case of, okay, let me just give you kind of a high-level idea. Actually, I don't want to get too deep into it. But for example, suppose it's the case that, no, you know what, I'm going to leave the suspense till tomorrow. But the fact that this sort of smears out, and there's lots of sort of intersections of different things, let me just give you a very high-level idea that, for example, this can be very useful when you're trying to encode data via error-correcting codes. That you will see a little bit, hopefully, if we can get to it, that this kind of gives you a way where, spoiler alert, this right-hand side is going to be like defining a bunch of parity checks that have to be satisfied. So for example, I'm going to take code words here on the left-hand side such that for every right-hand side, this determines that I need it to be that the parity of this plus this is equal to 0. And also the parity of this plus this and this and so forth is equal to 0. And without explaining really what do I mean there, in some sense, this is taking, so say I have some piece of data that I want to store, and I want it to be that if pieces of whatever I'm storing get lost, I can still recover. So what I should do is kind of store something where everything of the new item depends a little bit on multiple items of the original. And this, very loosely, is kind of giving a connection there. Okay, I'll keep it vague. Another property that follows directly-ish is that if you have an expander graph, okay, so that is pretty well connected, and in particular, the diameter of this graph is not too big. Okay, so what is the diameter of a graph? This is the maximum distance from any pair of vertices in the graph of how many steps, how many edges do you need to take to get from one to the other one. So in the extreme, for example, say my graph is a giant line, the diameter of this graph is n minus 1. Okay, because if I take one end of the line, I have to take n minus 1 steps to get to the other one, to the other end. In contrast, for example, if I have an expander graph, the diameter is roughly logarithmic in the number of vertices. Okay? And so why is this connected? You know, what does expansion really have to do with this? Well, this is very roughly. Suppose that I have two vertices in the graph. I want to figure out some bound on how far away they are. And what you can do for some, say, take some c roughly log n. What you can do is you can take this expanding property. Okay? So I start with u, for example. I know that the number of neighbors of u is something, and if I kind of take that set now of the step 1 neighbors, I consider this as a set S, and kind of look at what can I get in 2 steps. That's exactly like how many edges are going out from that set. Now I have a bigger set, but it's still, you know, not too big. I can use edge expansion. This is also expanding out. And you can ultimately show that if you go something like logarithmically many steps, at some point this distance t neighborhood is going to be strictly bigger than half the vertices. Okay, bigger than or equal to n over 2 plus 1. So I did this for one vertex u. The same thing holds for vertex v. And now we're done. Why are we done? Remember, I'm strictly bigger in each of these than n over 2. That means that these sets have to have an intersecting point. Okay? And that means that to get from u to v, in kind of the worst case, I travel t steps. Now this point is also distance t from the other one. Okay? Sorry, this is distance, yes, okay, this is correct, which means that the diameter, you know, okay, maybe it's times 2 or whatever, but this is still going to be order log n. Okay? Something that's actually quite related to this, and this I think is one of the really cool properties about expander graphs, is that it's what we call fast mixing, okay, via random walks. So the punchline of this is that if suppose that I start with a random vertex v, or kind of worst case vertex v, okay? Yeah, let's say worst case vertex v, any vertex v, and now I start a random walk. Okay, so in every time step I traverse exactly one edge, and the choice of which edge I take is just a random neighbor of wherever I'm standing. Okay, so for example, maybe I started 11, I choose the random over here, then I choose that random, and so forth. Then what it turns out is that, again, kind of roughly logarithmically many steps, where I end up. So this is a distribution, right? This is I'm starting at some v, okay? And over the kind of the random coins I'm tossing at each step, or the randomness of this procedure, there's some output probability distribution of where do I end up. Okay, so if I start here, then, for example, in step 1, okay, step 0, what's the probability distribution? It's 100% on where I'm starting, right? Now I take a step. Now there's d possible options where I could be, and each one has probability 1 over d. Okay? Now I take another step. Now this sort of splits the probability of each of these things. And in each step, it's kind of smearing out the probability a little bit more. To the extent that after enough steps, but not very many required, that I get the probability of these numbers, like what is the probability of each possible vertex, becomes very close to uniform. Okay? And remember, if you remember at the very beginning of the talk when I had this picture of like the blue and the red, the non-expander graph, and I said intuitively what's something that holds there, that if I start on one side and I take a random walk, think about what's happening to the probability distribution here. Well, it's sort of smearing out on this side, but there's much smaller probability. I have to be kind of lucky that if I even get to a vertex that has a neighbor over to the other side in order to cross over and start putting probability over there. Okay? And this, so out of interest, the proof of this, actually, one of the nice ways of proving it is by looking at the linear algebra interpretation. That this operation of taking this random walk, you can kind of view as an operation related to multiplication by the adjacency matrix. Okay. Good. I'm actually pretty good on time. So with this, I'm going to wrap up for today. And what are kind of the takeaways for you to keep in mind for tomorrow? So first of all, the high level, that there's these expander graphs. And roughly speaking, what these are, they're graphs that have strong connectivity properties, but they can do so potentially with very few edges in comparison to something like the Clique. Okay, and we saw, so these definitions, the edge expansion definition, we saw the spectral gap, this linear algebra-based definition of the difference, the gap between the top two eigenvalues. So a little bit about constructions and some useful properties. So for example, mixing via these random walks. And tomorrow, what we're going to do is we'll switch kind of from the foundations and actually start talking about where do these things pop up in protocols, in applications. Okay. So yeah, let me know if there's any more questions.
Okay, let's thank the speaker first.
Two questions. The first is related again to the random graph from before, because you said, okay, well, if we have a random graph, well, we choose uniformly random over the set of regular graphs, then we have an expander. I was thinking, if you look at just GNP, the standard Erdős-Rényi graph, well, your expected degree is n-1 times p, and you will be within that degree with very high probability. So if I just take a standard Erdős-Rényi graph with p, which is, I guess, capital omega of 1 over n, that should be good enough, right?
So the Erdős-Rényi graph, this is exactly the GNP that I was mentioning before. So one of the issues there is that in order to get like with high probability, that the p has to be kind of big. Like you'll have to have some sort of log term or something like this. Otherwise, there's a pretty big probability that one of the vertices will be unlucky, for example.
Okay. And the second question was about the mixing property of random walks on expander graphs. So the non-algebraic way of proving it, would it be via coupling in maybe?
Sorry, say that again?
If you try to prove the mixing properties of random walks on expanders, what would be a combinatorial way of proving it if you don't care about algebra? Would it be like defining a coupling, like another random variable and random walk and trying to couple the two of them, or would it be completely different?
There certainly exist combinatorial proofs. I'd have to think a little bit. I don't have one on the top of my head. But yeah, I mean, essentially, so there still is an intuition there, right? That kind of similar to what I said in the slide before, that you keep expanding, like your neighbor set is expanding out, that this at least gives an idea of why is this probability distribution starting to spread across the graph. About the specifics, that's a little bit, you have to be careful about the details and everything. But this at least is in line with the combinatorial type of proof approach.
Actually, I have a question as well. If you relax the deregular requirement to at least D? Does everything break down, or do some still results still?
I don't think it should be a problem, actually. There's some cases where it happens to be very convenient to have regularity, but it's mostly for convenience. I don't think that there's anything like truly fundamental that would have a problem.
Thanks for the talk. So I have a question about the last application for random walks. So maybe I missed it, but how important it is to even choose your initial vertex to be a random?
Yeah, it's actually not, I suppose. This is,
okay.
It was, in any case, what you end up getting, it's uniform independent of V, right? So maybe I should have just said, like, choose a vertex V. So this is true for arbitrary, like, kind of worst case vertices here.
So, okay, you get something much stronger. Even if you fix a vertex V, you get a uniform.
Yes,
okay.
Yes.
Thanks.
Okay.
Okay, thanks for the talk. Just curious, like you showed two definitions, but you mentioned like there are at least third. So like, can you tell about the third definition?
Okay, so the third definition is like an analog of okay, so what are the three main definitions? There's edge expansion, we saw, the spectral gap. And the third is also a combinatorial definition of vertex expansion. And it's sort of like an analog of how I define for bipartite expanders. That roughly, so here you don't have the bipartite structure, but that for S's of certain size, that the neighbor set of S does grow. And it's a little bit different from edge expansion, which just says that you have the number of edges going out are big. But for example, by the way, for edge expansion, it doesn't care if most of those edges are going to the same thing. But it turns out that these definitions, like you're good in one sense, kind of, if and only you're good in the other sense, but not exactly with the same numbers or parameters.
Thank you.